Hi, Shivraman. Hopefully you can hear me.
Yep.
Thank you. Hey, good morning.
Thank you. Yeah, thank you for organizing this.
Yeah. Hi, everyone. Good evening and welcome to the last talk of the session. We are very pleased to have with us Shivraman Balakrishnan, who is a professor with a joint department in the Department of Statistics and Data Science and in the department at CMU. His research interests are broadly in statistical machine learning and algorithmic statistics. His interests span statistics, optimization, machine learning, and information theory. Before rejoining CMU, he was a postdoc at UC Berkeley under Martin Wainwright and Bin Yu, and received his PhD also at CMU, the Language Technologies Institute, working with Jamie Carbonell. In the next 4 sessions, he will tell us about optimal transport. Over to you, Shivraman.
Okay. Thank you very much for the introduction, and thank you all for joining. Yeah, so I'll be doing 4 lectures on optimal transport, mostly on statistical optimal transport. So the first couple of lectures, at least, will be background on optimal transport. And I'll give you a little bit of motivation, and I'll talk a little bit about why these things are interesting and so on. Um, and then in the last 2 lectures, I'll talk about statistical aspects, which are how do you estimate various objects in the optimal transport framework given samples. Okay. Let me also say that if you have any questions, feel free to ask. I can sort of monitor the chat, but it's better if someone just interrupts me whenever you have questions. Okay. So maybe first let me just start off with some high-level remarks. So what is optimal transport about and why is it so useful? This is just very high level. So optimal transport, you should think of maybe at least at the courses level, it's a way to define a distance between or a bunch of distances between distributions. And these distances have with them associated mappings. So it gives you a way to map or transform one distribution to another. And those mappings have a lot of interesting properties, and the distances themselves have some way of incorporating an underlying metric structure. Um, as a result, the optimal transport has a lot of very deep connections to partial differential equations, convex analysis, statistics, machine learning, and so on. And we'll see a little bit of all of these connections. And there are many, many methodological and theoretical applications of the tools that one develops using OT. And so this is maybe some of the motivation for why one should learn a little bit about this field. Um, okay, so let me stop with the high level stuff and just get started with more concrete things. So the plan for today's lecture um, is going to be that I will tell you a little bit about the classical formulations of the optimal transport problem. So this goes back to the late 1700s, so it's many hundred years old. And then I'll tell you what Wasserstein distances are. And then finally, I'll tell you a little bit about connecting different formulations of optimal transport. And then if we have time today, otherwise in the next lecture, I'll tell you about some of the theory of duality that comes up in optimal transport. Okay, so let me first start off with the historically original formulation of optimal transport. Um, it goes back to 1781 and was formulated by Gaspard Monge. So this will be called Monge's formulation. So Monge had the following question. He was wondering, if I give you a pile of sand, what is the most efficient way to move that sand to fill up a ditch? So the mental picture you should have is that he had some pile of sand and somewhere else there was a big ditch. Right, so this is your pile of sand and this is your ditch. And what he was wondering was, what is the most efficient way to move this pile of sand into this ditch? So for us, we will just, okay, the pile of sand and ditch have to have the same volume, so we'll just normalize that volume to be 1. And then we'll think of this as a pair of distributions. So this will denote as the distribution mu. This one, sure, you flip it, and then this is the distribution nu. And so what it is that Monge was asking for was a way to transport one of these distributions, which is the pile of sand, into another, which is the ditch. So what does it mean to transport sand here? So transporting sand meant the following thing. I have to tell you where to move each bit of sand. So that is, I have to construct a map. Let's say these distributions more generally live in RD. So it goes from RD to RD. And what does the map do? It prescribes where each atom has to go. So for each X, it says, take this pile of sand, take whatever sand is at the location X and move it over to a location T of X. Okay. And for it to be a valid transport map, it should be the case that um, you must satisfy a sort of technical condition. Let me write it out for you. So what does it mean to be? So this is just defining how you transport things. For it to be a valid map, it has to actually push the first distribution onto the second. So that is, we'll write it the following way. So let's now think about our two distributions. If I take some set A here, so this is my set A, and I look at its pre-image, so where it came from, so that's maybe the mass came from here, this is T inverse of A, then it must be the case that the measure mu, if I look at how much mass is in the set T inverse of A, it should be equal to how much mass went to the set A. Right? So this is what it means for every set A. Okay, so if you satisfy this condition, then you're actually transporting the mass mu to nu through this map T. Okay. And maybe it's worth somehow, maybe the more intuitive way to think about this condition is the following. If I give you a random variable x with distribution mu, then if I give you a valid transport map, it must be the case that T of x has distribution nu. Okay, so this is what it means to be a transport map between this pair of distributions. Is everyone okay so far? Okay, great. And so, okay, so what did Monge want to do? He wanted to minimize the cost. So now we have to say, okay, if I give you a transport map, what is the cost that it's incurring? So it's going to take each piece of sand from location X and move it over to T of X. So we can define some distance between X and T of X. For now, we'll stick with the Euclidean distance. So the cost for moving some point X to some point T of X we'll just define to be the Euclidean cost, the Euclidean distance between X and T of X. Okay, so Monge roughly was asking, find me a transport map. So it's something that satisfies a set of conditions that minimizes this cost. And this cost is defined for each atom, so maybe you want to minimize the average cost. And so all of this will lead us to our first formulation of the OT problem. So this is maybe how Monge has originally formulated it. Okay, so he wanted to say, find me a map T such that it is a minimizer of an optimization program. It's the minimizer over all valid transport maps. So I will use the following notation, some standard notation. It says T pushes mu onto nu. Right? So this is shorthand for this condition up here. And so Monge was trying to say, find me a map that minimizes the expected cost or the average cost, which is just x minus T of x d mu. And so this one will be our first and important formulation of the OT problem. So he defined some cost for moving mass around. And then he said, what does it mean to move mass from one distribution into another? That's defining this transport map thing. And then the goal in optimal transport is to find somehow the transport map that minimizes this cost. Okay, let me take a second to pause here. Just make sure there aren't any questions so far.
I don't think there are any questions.
Okay, very good. Thank you. All right, and so now that we've defined some optimization program, it's worth trying to understand a little bit about its structure. Um, so maybe the basic questions that one might have is first, are there always valid maps? And then maybe if there are always maps, are they always unique? Are they always stable? So if I perturb this problem in some way, what happens to the transport map? Maybe you care about its regularity. Is it smooth? What can I say about the map? Right? So more generally, what can I say about the OT map? Is it stable, regular, unique? Okay, and maybe eventually, what does this have to do with statistics or machine learning or anything else? Okay. Um, so the first thing to observe is, okay, there are two sort of downsides to this formulation. The first one is that um, the constraint, right? So in this program, which is that t has to push forward mu on, onto nu, um, it's a very nonlinear, non-convex constraint. And so it's just not a nice constraint. And one way to try to see that is imagine that the distributions mu and nu had some densities, then this constraint is encoding for you what we would call the change of variables formula. It's sort of saying that if I look at mu of x, it should be roughly, should be something like nu of t of x times some Jacobian term, which is something like the determinant of the gradient of t. And so this is and must hold for every x. At least if the distributions are nice, then your constraint that t is pushing forward mu onto nu is actually encoding the change of variables formula. It's saying it must satisfy this constraint. Okay, so that's one thing to notice, that it's just not a very nice constraint. The other thing to notice is that maybe the set of maps is empty, right? So there is not always a solution to this program. So maybe the classical example is you imagine I start with a distribution, say, which is a point mass at 0. Right? So this is just my original base distribution, it's just a point mass at 0. This is mu. And let's say I want to transport it to 2 point masses, say at minus 1/2 and plus 1/2. So this is my target nu. And so the thing to notice is that, okay, any map can only map this point 0 to 1 point. So there's no way that a map can split atoms. And so there is no valid map here. To define a valid map, we need to split atoms. Okay, so let's back up for a second. We defined a formulation of optimal transport. It was just some intuitive formulation that said, I want to transport one distribution to another, and I want to minimize some associated cost. And then we said, okay, here's an intuitive looking optimization problem that seems to capture what we want. And then we made some observation that, okay, if I viewed it as an optimization problem, it doesn't have a very nice constraint set. and the constraint set could be empty. There could be no solution to this problem. And so now one has to wonder, okay, how does one make progress here? And so Monge introduced this formulation in the late 1700s, and it sort of sat dormant for these reasons that it's not very easy to study this program. It sat dormant till something like 1941, when Kantorovich gave a different formulation for the OT problem in a very classical two-page paper. So now we will discuss this other formulation and see what its relationship is. Okay, so this is now, that was Monge's formulation, and now we will talk about Kantorovich's formulation. Um, so Kantorovich said, let's first define the set of couplings between the pair of distributions. So define, okay, so let's think about a coupling of our pair of distributions mu and nu. We'll denote these by gamma. Right, so what does it mean to be a coupling? A coupling is just a joint distribution. So it's just a joint distribution on our two probability spaces, which has, let's say, the first marginal of gamma is mu, and the second marginal is nu. Okay, so if you prefer it written slightly more formally, it just says that if I look at gamma, it's a joint distribution on RD cross RD. And it says, let's suppose I take any set A and I look at gamma of A cross RD. This must be equal to mu of A for all A. And the same way, I looked at gamma of RD cross A, it should be equal to nu of A. Okay, so this is just, think of it as you can associate with mu and nu two random variables. I'm going to put down a joint distribution defining those two random variables as joint distribution. And for it to be a valid coupling, I just require that the first marginal should have the same distribution, say, as x, and the second marginal should have the same distribution as y. Okay, so this is just a standard object. It's just a joint distribution which has specified marginals. Okay, so now you can say, we'll denote the set of all couplings as capital gamma. Then we can say, okay, I will associate with my coupling some cost. And then Kantorovich said, okay, maybe you should find the coupling that minimizes the cost. Okay, so rather than look for a map from the first distribution to the second, I will look for a coupling between them. And I will, again, try to minimize this cost of the coupling. So this is now maybe Kantorovich's program. Just says, let's look for the coupling. So let's find some special gamma, which minimizes the following thing. We'll look at the inf over all couplings. So this is a valid coupling of our pair of distributions mu and nu. And then I will define a cost, which is just the, let's say, x. Let's stick with the Euclidean cost, but you can put any other cost you like. So the coupling sort of says for every x, you can view it as giving me a distribution over y, and it says where should I move the mass? And so I say, okay, the cost of my coupling is the average, the expected distance that it moves things around, again, integrated across gamma. Okay, so this was Kantorovich's formulation. So this is just an alternative formulation of something that resembles our optimal transport question. Rather than look for the optimal map between the two distributions, we're looking for the optimal coupling. And now let's again think about this one and say, okay, when is there a solution and what can I say about it? Okay. If you have questions about the formulation, maybe now is a good time.
Yeah, there are some questions.
Okay.
Hello, am I
Sorry.
audible?
Yeah.
Hello. Yeah. So my question is that if you like scroll a bit up to the Monge's formulation,
Yeah.
uh, are there any conditions on T, like should T be smooth, continuous, or differentiable or something? You wrote the Jacobian of T, the determinant of the Jacobian. Why should that be defined in the first place?
Yeah. So I'm just saying if it were defined, then this would be the constraint. There isn't a, okay. Yeah. So you should not think of this as always being possible. So it encodes change of variables whenever you can make sense of that expression. It's not always the case that you can, and then it will not make sense. So yeah, this was not meant to say that T has to satisfy this equation. It's just if it so happened that there was a nice smooth map between them, this is sort of it's just giving you some intuition for what the constraint is trying to encode.
Okay, so I have another question as a follow-up of what you said. If, say, mu and nu are both continuous, can it happen that the optimal T is not continuous, the optimal coupling?
Yes. So I guess there are classical examples where, I don't know, you can imagine, I guess you have to say what exactly one means by continuous, but you can imagine that mu is like the uniform distribution on this object, and then, I don't know, nu is something else. It's the uniform distribution on some other object. Maybe you smooth it out a little bit. It'll
Oh,
still be the case that the optimal map will have to kind of move half the mass here and half the mass here, and it will be discontinuous. So there is a lot known about the regularity of the OT map. It is not the case that somehow you need conditions both on the distributions and their support in order to say something like T is smooth.
got it. Thank you.
Okay. Any other questions?
Uh, there's one more question.
Is mu a probability measure?
Yes. Mu is a probability measure and nu is a probability measure.
So the determinant expression would have a mod sign.
Yeah, you are correct. Sorry. Yeah, that's correct. Put this here.
Yeah, thanks.
Thank you.
Thanks. I think there are no more questions. Please continue.
Okay, thank you. Okay, so very good. So now let's try to stare at Kantorovic's program and see uh, what are some properties of it. So let me just make some remarks. So the first thing is that the constraint set is very nice now. So constraint set is nice. So what do I mean by this? So maybe the way to okay, so what is the constraint encoding? I claim that all the constraints are linear. So and in fact, the whole program is an infinite dimensional linear program. So it's a potentially infinite dimensional uh, linear program. So what does that mean? The objective is linear in the variable gamma, and the constraints are also linear in the variable gamma. So the constraint, maybe you should, again, think of it as saying the integral over Rd of gamma xy equal to, it says these marginal constraints. It's just saying it should be equal to mu of x. Right, so you have a bunch of constraints like this. Again, maybe it's easier to imagine this in the finite dimensional case. So if your two measures had finite support, say, then the couplings are just matrices. And it's just saying every row of the matrix should have a certain sum and every column of the matrix should have a certain sum. So that's one way of viewing what's going on, but maybe just let me make this claim for now. It's just that the constraint that it's a valid coupling is something of this form. It's a linear constraint. And there's analogous ones that say, okay, if I integrate over sorry. Yeah. Okay. So you're encoding some constraints on this one. The other thing to notice is that there are always valid couplings. So for instance, the coupling that just independently samples X and Y, so that is, imagine I draw X from mu and Y from nu, and I put them together, this defines something. It's called the independence coupling. This is always a valid coupling. So maybe to contrast with Monge, there is always at least one solution to this program, and the constraints are very nice. They're linear. The entire program is quite nice. It's for any cost that I can put here, it is a linear program. Okay. And this will be somewhere at the heart of how we think about duality and so on. Okay, so now there are maybe these two formulations. Maybe one could argue that Monge's formulation is a little bit more intuitive because it prescribes to you a clean way to transfer one distribution to the other. And maybe Kantorovic's formulation, you have to think about couplings. If you're not used to thinking about them, they are not defining maps. They're defining what you would call Markov kernels. So for every x, it's giving you a conditional distribution of where to move the mass. So it's maybe a little bit harder to interpret. So that's perhaps the downside of Kantorovic's formulation. All right, so to build some more intuition, let's talk about a simple case. It'll come up a few times for us. It's a case which has been studied a lot and has a lot of structure. So we'll think about the case. We'll call it the discrete case. And we'll just try to see what Kantorovic's program looks like. Okay, so what do I mean by this? I will take the simplest possible case where mu is just a set of n atoms equally weighted, let's say. None of this is particularly crucial, but this makes it just transparent to see what's going on. So there's some n atoms xi. This is maybe your picture. And this defines the first distribution, and I'm trying to map it to some other set of n atoms. Let's call them yj. So this is the case. So this defines the distribution mu, this defines the distribution mu. Okay, so now we can like explicitly write out what Kantorovic's program is and what the constraints are. So as I said earlier, in this case, we are looking for a coupling. A coupling is just a joint distribution on these 4 x atoms and say 4 y atoms. So it is a matrix. So gamma is now going to be a matrix. In this case, it'll be an n cross n matrix, let's say. And what do we know? It must satisfy a bunch of constraints. So gamma ij has to be positive. And so these are now the constraints. And the sum over j, gamma ij, should be 1 over n. Similarly, the sum over I of gamma ij should be 1 over n. For every, this is true for all j, and this is true for all I. Right, so these are the constraints that the marginals are what I want them to be. And so these are my marginal constraints. And as you can see, as we said earlier, these are linear constraints. And what is my objective? My objective is just the objective. I'll define something, which is the cost matrix. It'll just say CXY is the, let's say, distance between X and Y. So then the objective looks like this. The objective is the sum over I and J, gamma ij, times the cost of moving xi to yj. Okay, so I would like to minimize this subject to these constraints that gamma satisfies up here, which is that gamma is in subset gamma. Right, and so now you can sort of very clearly see this is a linear program. It's linear in the gammas. The constraints are all linear in gamma. Okay, and maybe let's think about this for a second, right? So what are the constraints really telling me? They're telling me that, so this polytope, it's defining a polytope. It has a name, right? So it is, maybe one would call this the Birkhoff polytope. The polytope itself is sort of the, okay, up to some scaling of 1 over n, it's the convex hull of the set of permutations. And so you should imagine what are permutation matrices. They are matrices where every row has exactly 1, 1. So it's a 0, 1 matrix. So every row has 1, 1. Every column has 1, 1. So that's a permutation matrix. You take the convex hull of all of them and maybe scale it by 1 over n. And then you get this set gamma. Okay, so you should intuitively think about it as you're solving a linear program over the set of permutations. So where is this permutation thing coming from? What you're asking when you solve the OT problem here is you're saying, find me the best way to transport these 4 atoms to, say, these 4 atoms. This will amount essentially to finding mappings or matchings from the first set to the second set. So maybe the best way to uh, minimize this cost is you say move x1 here, move x2 here, maybe move x3 there, and move x4 here. So it amounts to finding a matching between the x and y atoms, right? So that is the set of permutation matrices. And okay, maybe if you've seen linear programming before, there's some polytope which is defined. So these vertices of these polytopes, of this polytope is the set of permutation matrices, and then there's some cost. And so you can say that, okay, the optimizer has to be one of, okay, a vertex is always one of the optimizers of this program. So that is, what you're saying is that there's always a valid matching between them that optimizes this program. Okay. So this also tells you that, so maybe this property is not so directly obvious, but it tells you the following thing, that Monge's problem also has a solution here. Always has a solution in the discrete case, in this particular discrete case. Yep.
How is it the set of permutation matrices?
How is what the set of permutation matrices?
You said gamma was the set of matrices, or
No. I said, so it's called the Birkhoff polytope. I didn't sort of prove this fact to you, but I'm saying that the set of permutation matrices is the vertices of this
right?
polytope. And I'm saying this polytope you can think of as, okay, ignore the scaling of 1 over n for now. Right? If I replaced all the 1 over n's by 1, it says every row sums to 1, every column sums to 1. These are doubly stochastic matrices.
Right.
Doubly stochastic matrices are exactly the convex hull of the set of permutation matrices.
Yeah. All right.
Okay, so let's back up again for a second. So we're just saying in this case, the Kantorovich problem has a very nice structure. It's an LP it's an LP over the convex hull of these matchings. We also know somehow structurally that there will always be a valid matching that will optimize this LP. So you can think of it as looking over the set of possible matchings from X to Y and finding the one that minimizes this cost. As a consequence of this fact, you will realize also that Monge's problem, which is to find a map from X to Y, also has a valid solution here, and it's exactly the one of these permutations that or matchings that optimizes Monge's problem. Okay, so this is maybe just to give you some intuition about what Kantorovic's problem looks like. So now let's move on. If there are no questions, I'll move on to the next thing. Okay. Good. So far we've defined two versions of the OT problem, the Kantorovich problem and the Monge problem. And now finally, we'll define something that will be central to us for the rest of this, which is just what is the Wasserstein distance? Or what are Wasserstein distances? Okay. So you can take Kantorovich's program and use it with any cost you like, but maybe the most convenient cost to think about is the LP cost. So let's just think of the case where the cost of moving X to Y is given by the distance, the Euclidean distance between X and Y, let's say raised to the pth power. Okay. So then it'll turn out if you use costs of this form, then we can define the optimal value to Kantorovich's program, and it will define for us a metric on distributions. So given mu and nu, I can define the following thing, which is we'll use the notation WP. It's the Wasserstein distance between mu and nu to be, okay, we'll need the condition that I guess mu and nu have to have finite pth moment for this to be well defined. So suppose your two distributions have finite pth moment, then you can define this thing, which is the cost of Kantorovich's program. Okay. And this defines something. Right, so this is just, we defined an optimization program which said, what does it mean to couple one distribution to another? And now you can say, what is the cost of that coupling? And the minimal cost coupling defines some cost, and that is the Wasserstein distance. So the Wasserstein distance, at least intuitively, is just the cost of the best coupling. Okay. And we should spend some time talking about this because it is one of the main reasons why the OT framework is useful. So some things that are true, it's a metric on distributions. The other thing that's true is that it defines a distance between distributions that respects the underlying Euclidean structure. So what does this mean? And maybe this is one of the most important features, respects the underlying metric structure. So let me give you an example to try to illustrate what this means and why this is a useful property. So imagine you have a source distribution mu, and it just looks like a pair of atoms, say at -1/2, and let's say at +1/2. Okay, so it's like has mass half here, let's say half here. And let's say I sort of perturb it a little bit. And what do I mean by perturb it a little bit? It could mean many things. But let's say what I actually do is I move the mass to, let's say, half plus epsilon, let's say minus half minus epsilon. So I put the same amount of mass here and here. Right? So the original distribution was here and here, and I moved the atoms just a little bit, and I got this other distribution nu. Right? So you could say, okay, so let me try to define some distance between them. We can think of very classical statistical distances, so things like the total variation distance between mu and nu, or the KL, or if you like, the chi-squared or the Hellinger, any of these classical statistical distances. So the TV distance, for instance, between these two will actually be 1. Right? So even though I perturb the atoms just a little bit, the TV distance doesn't care about this. The fact that now they're putting mass in different places just means the total variation will be 1, and the KL distance will be infinite, and so on. Right? So all of these distances will take somehow their essentially maximum possible value here. And so somehow what's going on is that they don't care about the underlying structure. They only care about how much mass is at each location. So each of these statistical distances only cares about how much mass is at the location. It doesn't somehow understand that there's an underlying metric, and I've only perturbed the distributions by a very small amount according to that metric. On the other hand, if you can calculate the Wasserstein distance here, so let's say the W2 distance between these two distributions will be very small. It'll be something that maybe less than epsilon squared. Right? So in some sense, the Wasserstein distance is sensitive to this fact that there is an underlying metric. And so if I move atoms just a little bit according to that metric, the Wasserstein distance will not blow up. Okay. Is everyone okay with this property? It's about this property of Wasserstein distances is very important.
I have a stupid question. So
Yeah.
is there a reason for writing the two both in the subscript and superscript?
Yeah, so yeah, the Wasserstein distance, so this is the Wasserstein distance raised to the power p. So maybe this is the correct definition of the Wasserstein distance. You should put the 1 over p on the right-hand side, and then this is an actual metric. If you raise it to the pth power, it's not an actual metric, but so the definition of the Wasserstein distance is what is now written here.
Okay, I guess one more stupid question. So when you say the norm of x minus y to the power p, do you mean the L2 norm of x minus y to the power p, or do you mean the pth norm to the power p?
I mean the L2 norm to the power p. You can do it with any norm and it will share some similar property. So, but yeah, so when I say W1, I mean you take the Euclidean norm and raise it to the power 1. And if I say W2 squared, I mean Euclidean norm raised to the power 2.
Thanks.
Excellent. Okay, so let's
There's one more question. Sorry.
yeah, go for it.
So sorry, this is again about that Barkov polytope. So there is this set of couplings, and there is this set of this convex over all permutation matrices, right? And every permutation matrix one can think of as it's like a map from this n points, n x's to the n y's. So I mean, is there any easy intuition to say like how couplings are connected to this like distribution over these maps?
So let me back up. So I'm saying that couplings are like every permutation is a coupling between these two distributions.
Every permutation is a map, right? Like from one set of endpoints to another set of endpoints.
Yes, but I'm saying it in this special case, it's also a coupling. So that is
Yeah, that's true. Yeah. So what I'm saying is this Barkov's polytope is like is a set of all distributions over this potential maps, right? from endpoints to another set of endpoints. And that is somehow also equivalent to the set of couplings. Uh, is-
I don't think you should think about, I mean, what you said is also correct, but okay, the way to think about it is that there's this set of matchings, and then there are the set of sort of blurry matchings. So what is a blurry matching? I take this point and I say move half of it here and move half of it there. Take this point, move half of it, uh, and so on, right? Like I can sort of imagine splitting atoms. That is the set of couplings. So couplings define sort of blurry matchings from the source set to the target set. They allow you to sort of split the mass of any point arbitrarily as long as you end up at the end of the day with a full 1 over n at each of the points.
Hi, I have another question. And
Yeah.
so other than the case of empirical distributions that you demonstrated, are there any other case where the Monge's program and the Kantorovich program gives the same output? Like it's not obvious to me if they should or they should not be the same.
Yeah, and so that will be the focus of the next part. When I tell you about some connections, there is actually a very broad and interesting collection of problems where they will give you the same answer. Yes.
Okay, got it. Thank you.
Okay, excellent. Other questions? Anything about Wasserstein distances and sort of trying to sort of the contrast with KL and TV?
No more questions.
Okay. Okay, so then let's move on to the next thing. And this one is how do we connect Monge and Kantorovich? And like, so what is known about the two, right? So Monge and Kantorovich, like what is the connection between them? More generally. So I gave you one example, which is the discrete case where at least if they have the same number of atoms, they coincide. But one can ask more generally, what is the connection between them? Okay, so I will tell you one theorem. So this is the case when, let's do the case when P is 2. Right? So this is the Euclidean squared cost, right? So the cost is squared Euclidean. This is the case when there's the most beautiful theory known. So almost all of the rest of the lectures will kind of focus on this case, squared Euclidean. And so here there is a very beautiful cornerstone result in OT theory, which is called Brenier's theorem. And it says the following. Suppose that your two measures mu and nu both have finite second moments. This is the thing I require to be able to somehow think about Wasserstein distances and so on this in this case. So they have finite second moments. And here's the main assumption that mu has a density. Right? So you should think of this. So we've already seen an example where Monge and Kantorovich will not agree, which is when I'm taking one atom, say, and trying to move it to two atoms. So the way that we'll avoid that counterexample is to say that mu has a density. So you should think of mu as some sort of continuous distribution. And this is the only assumption being made. So once you do this, Brenier's theorem will give you a sequence of conclusions. Right? So the first and maybe most important is that there is a map, we'll call it T0, which pushes mu onto nu. Right? So Monge's problem, if mu has a continuous distribution, then Monge's problem has a solution. So, and there's a map, it does this. Okay, let's say T0 is optimal for Monge's program. And there's also a very important and nice structural property that it has, that T0 will always be the gradient of a convex function. Right? So phi 0 is a convex function. And we will talk about this property at length in a minute, but this is just a statement for now. It just says that Monge's program has a solution. That solution has the form that it will always be the gradient of a convex function. And also, I don't know what the gradient phi 0 is, it's a unique solution. At least, if you want to be precise, maybe it's mu almost everywhere. So again, if you want, you can ignore the measure theory part of it, but it's just saying that there is a unique, essentially unique solution. This convex function, at least up to shifts, is a unique thing. Okay. And it also says the following, that Kantorovic's problem also has a unique solution, and the two are related, right? So there is an optimal coupling gamma 0, which solves Kantorovic's problem. And gamma 0 has a specific form, which is that gamma 0 is the one that the coupling induced by Monge's map, right? So it is of the form x and the gradient of a convex function at x. Right? So it is induced by a map. It's a coupling that is in some sense degenerate. It is of the form of a map. It says take x and move it to grad phi 0 of x. Okay. I will also just maybe briefly remark something which, okay, so this as stated is Brennier's theorem. So you can also ask about under what conditions can I go back? Can I move back from nu to mu? And so I'll just state some fact now. It'll be useful for us to know later on, which is just if nu also has a density, then there is again a map that maps it back that solves Monge's problem. And that map will have the form, so we'll call it S0, which pushes nu now onto mu. And S0 will turn out to be the gradient of the Fenchel conjugate of phi 0. Right? It will be the gradient of phi 0 star, where phi 0 star, if you've not seen it before, it's just the convex conjugate of the function phi 0. And this quantity looks like maximize over x transpose y minus phi 0 of x. And so it is maybe not so important yet to understand what this is if you haven't seen Fenchel conjugates before. It's just some sort of dual function to phi 0. It's also a convex function. And so Monge's theorem would say, okay, not only is there a map to go from mu to nu, if nu is nice, then there's a map to come back from nu to mu, and it's related to the forward map in the following way. Okay, is everyone okay with the statement of the theorem?
Yes.
Okay, very good. So maybe the thing to spend some time on is to understand why are gradients of convex functions arising in this case and what is special and interesting about them. Okay, so now we'll just say, okay, what is this condition saying? Why is it nice? Okay, and the way to think about this is that just the gradient of a convex function is the oh, sorry, someone, yeah. Go for it.
Uh, is it okay if the densities have like Dirac deltas and stuff?
No, so that's what it
Like
means
proper
to
densities.
yeah, it has to be a proper, absolutely continuous density. Yeah.
Thanks.
Okay, so let me just say what the punchline is. The gradient of a convex function you should think of it as satisfying somehow some multivariate notion of monotonicity, right? So and I'll tell you what this is in a slightly more precise sense in a second. Okay, so at some high level, this is encoding some very nice structural property of the optimal transport map. The optimal transport map will satisfy some multivariate notion of monotonicity. So in some sense, because it's optimizing this cost, it will not do something inefficient. It will never kind of move mass from, let's say you're on the real line, it will never move X to Y, but if I move a little to the right, it moves to the left. So the arrows of the map will never crisscross. Right? So there's some sense in which uh, it's encoding that the optimal map has to have some nice monotonicity property. Okay, so now let me just clarify, if you haven't seen this before, why the gradient of a convex function satisfies some intuitive notion of monotonicity. So let's start off in 1D. So in 1D, what does it mean for a function to be convex? It looks like this, and it just says this line has to be below the function. So in 1D, I can write out that convexity of a function means that, say, phi of y, let's think this is y and this is x, has to be at least phi of x. Plus, you can say gradient or subdifferential, if you want to be precise, but let's say subdifferential. So it has to satisfy this equation for any pair x and y. So I can also flip it and say, okay, it must be the case that phi of x has to be at least phi of y plus. So I get these two inequalities for every pair x and y. Yeah. Sorry, you have a question?
Yeah, so in the case of subdifferentials, again, I have a multi-valued map, and that again is not allowed according to Monge. So
No, you should. So it is not allowed. So it can be subdifferentiable. So you just have to be a little bit careful about the measure theory. So any convex function is differentiable almost everywhere.
uh-huh.
And this is just a statement. So when you say, when I use notation like this, I only need to define this map mu almost everywhere. And I'm saying that this function will, any convex function, even if it's only subdifferentiable at some points, it will be mu almost everywhere differentiable.
Yeah. Sorry, I missed the part that there is the density here, so you don't have to worry about splitting atoms and stuff. So yeah, sorry.
Yeah.
Hi, I have a question.
Yeah.
In the expression 2, you wrote that gamma 0 equal to x comma grad phi naught x. But isn't gamma 0 a real valued function from like a joint, like a tuple to a real number? Isn't that what gamma 0 is supposed to be? A joint?
I have to define a joint distribution on RD cross RD. I'm saying this pair defines, so if you think of these as random variables, they define some distribution on RD cross RD. Yeah,
Okay.
this is maybe not the ideal notation, but this is, I'm just saying, think of the case x drawn from mu and mapped to grad phi 0 of x that defines a pair of random variables that has a joint distribution on RD cross RD. Call that thing gamma 0.
Okay, got it. Thanks.
Okay, so let's go back to this case. Okay, so once you have this pair of inequalities, you can just sum them up and you will arrive at the following fact that if I give you a convex function, it will always be the case that grad phi of x minus grad phi of y. So we're in 1D, so then times x minus y has to be positive. Right? So if I just sum these two inequalities, I'll end up here. And this is just saying that this map is monotonic. So this is a different way of saying that if x is bigger than y, then phi of grad phi of x has to be bigger than grad phi of y. Right? So this is the gradient of a convex function phi is monotonic. Okay, so Yeah, so and the multivariate generalization of this would be something which is, I will just define it for you. It's maybe not so important. It's called cyclical monotonicity. So if I take some collection of points x1 through xk and I imagine going through them in a cycle, and then I go from here back to the first point, you can sum up a bunch of inequalities like this, and it will say that for any cycle x1 through xk, it must be the case that the sum, so any convex function's gradient will satisfy this property that xi minus. So I'm just going to walk through the cycle. Some of these gradient terms will cancel out. But you will satisfy this condition. Okay, so, and this is called cyclical monotonicity. So this is some multivariate analog of usual monotonicity, and it is something that is satisfied by the gradient of a convex function. It turns out that there's a converse to this theorem, which is that any map which is cyclically monotonic lives in the gradient of a convex function. So you can define it, you can find some convex function whose gradient looks like any cyclically monotone map. Right? So there's some very close connection between things that are cyclically monotone and gradients of convex functions. Okay, so now maybe going back to Brenner's theorem, it just tells you, okay, there's this optimal transport map. As long as mu has a density, there is a unique OT map, and the OT map satisfies this very strong notion of monotonicity. It is the case that the OT map will always be the gradient of a convex function and is in some sense always going to satisfy this cyclical monotonicity notion. Okay, let me pause again for a second and see if there are more questions.
No questions.
And how much time is left for today?
You have another 12 minutes.
12 minutes. Okay, so then maybe I will spend this 12 minutes starting off duality, and then we'll go a little bit deeper into duality in the next lecture. So, okay, so let me do duality. Okay, so let's say, let me just get to the punchline first, which is, so we've defined this convex program. This is Kantorovic's linear program. Because it's a linear program, you can think about the LP dual to it. And in fact, historically, this is why Kantorovich actually came up with duality. He devised duality as a means to study this optimal transport program. And so the LP dual to the OT program will reveal a lot of structure about it. And we will use various facts about its dual at some point. And so I'll tell you a little bit about the duality. So maybe as a first thing, I'll just today derive the dual in the discrete case. So this is for Kantorovich's program. And we'll do the discrete case that I just wrote down. So again, we're thinking of the case where there are n atoms on X and n atoms on Y, and you're looking for a coupling between them. So let me try to write it out again. So this was the primal LP, right? So the sum over ij, gamma ij times, we'll just keep it with some general cost for now. So times Cij. So this was Kantorovich's programs that minimize the cost of your coupling, subject to the following constraints. The sum over I, gamma ij should be 1 over n for every j. And then similarly, the sum over j, gamma ij should be 1 over n for every I. Okay, so this and okay, gamma ij has to be positive. So these are my constraints. This is my LP. I can just try to derive its dual. I will do so in the usual Lagrange duality way. So we'll write out its Lagrangian first, and then we'll optimize out the primal variables. So the Lagrangian here looks like this. It's the min over gamma, the max over, okay, so there are, I'll associate, let's see, these with some Lagrange multipliers alpha j, these with some Lagrange multipliers beta I, and these with some Lagrange multipliers delta ij, right? So there are Lagrange multipliers associated with each of these constraints, and let's see. So we are going to maximize over alpha and beta, they're free, and the delta, which are all positive. The sum over ij, gamma ij, oops, Cij, plus the, so let me do it with a negative sign maybe. So minus the sum over j, lambda j times 3. Oh, sorry. And then there's minus delta ij gamma ij. Right, so this problem here is the Lagrangian. It's equivalent to the original thing, and it's an LP, so we know that strong duality holds. So I'm going to imagine swapping the min and the max, and then minimizing over gamma. Right? So when I minimize over gamma, I will get out my constraints. So you take the derivative of this expression with respect to gamma ij, so you will end up with the fact that, so the constraints for my dual are just going to be of the form gamma ij minus alpha j minus beta I minus delta ij should be 0. Right, so this is just take the derivative of your objective with respect to gamma, set it to 0, you'll end up with this constraint. And then when you plug this back in the objective, all the terms involving gamma will drop out. So, and the objective is just going to be to maximize over alpha and beta the sum over j, alpha j divided by n, plus the sum over I, beta I divided by n, subject to this constraint. Remember that delta I has to be positive. So from here, you will end up with the fact that alpha j plus beta I, oops, sorry.
Sir, should that be C? Yeah.
Thank you. Should be less than Cij. Okay, so the constraints are encoding this. When I say the delta has to be positive, then it will end up looking like this. Yep. And so this is the dual to the Kantorovich linear program. And so now let's just interpret it for a second. It's just the following program, you maximize, so I give you the costs, you maximize over vectors alpha and beta. They're all of length n. And I look at the sum of alpha j and the sum of beta j, and I divide it by n, and then the alpha and beta have to have this constraint that their sum should be less than Cij. So this maybe doesn't make so much sense. So let's just interpret it for 1 second. So this is sometimes called the shipper's problem. So what you should imagine is the following. Originally, I wanted to transport this distribution from, I don't know, I had these points xi and I had to move them to these points yj, and there was a cost for moving xi to yj, which was Cij. And now I don't want to handle the shipping myself, so I contract a shipper. And this shipper comes to me and he says, I will charge you, I don't know what, something, alpha j to load, or maybe, okay, so maybe this is to unload, and beta I to load at the point xi. So this to load xi must, and to unload at the point yj. So this shipper comes to me and promises me something. He says, I will do the shipping for you. I will transport your first distribution to the second, and I will charge you alpha j amount to unload at some place yj and beta I amount to load at the location xi. Right? And now, if you are the person who originally wanted to transport, you would say, okay, this seems like a good deal for me if the sum of loading plus unloading costs is less than the cost that it would have cost me to ship this myself. Right? So the shipper needs to satisfy this set of constraints to in order for me to accept this deal. Right? So I'm the one who originally wanted to transport these distributions. As long as the shipper can produce for me these loading and unloading costs, which are favorable, that is, they are less than the cost I would incur shipping it myself, then it seems like a good deal. So on the other hand, the shipper is trying to maximize his profit. So he wants to make alpha i's and beta i's as large as possible. So the shipper will try to solve this dual LP and set the prices alpha I and beta j. As long as he satisfies these constraints, it's a good deal for me. And so that's the interpretation of the problem. So the shipper will solve the dual. And as long as, and now maybe, okay, strong duality will tell you something here. So strong duality will say that a clever shipper can extract the entire amount from me. So the clever shipper can set prices alpha and beta so that they extract the full cost, so that I pay as much as it would have cost me to ship myself. Full cost. Okay, so this is maybe the way to think about it. We'll come back to this dual and we'll interpret it in a lot of other cases. But in the discrete case, this is how you would go about it. You would write out what the Lagrangian is, you would optimize out, and you would end up with another LP, which is this dual LP. And strong duality will tell you some nice structural property. So the dual has some interpretation as what a shipper would solve, and strong duality will give you some nice guarantee in this case. Okay, so let me stop here for today, and I can take some questions about the last part.
There's one question.
In the last term of the Lagrangian, is there a double summation?
Yeah. So you're saying here, there's a sum over branch. Yeah, thank you. So there's a sum over I here and a sum over j there.
Can you go to Brenner's theorem where you explained that mu is has a density which is absolutely continuous?
Yeah.
Yeah. Can you give some measure theoretic interpretation as to what blows up when we remove this assumption?
Yeah, so I guess maybe we've seen a counter example, right? So that is, if you imagine trying to move one atom of mass to two atoms, there are no solutions to Monge's program, right? So you shouldn't be able to characterize the solutions unless you make some assumption of the form that at the very least, there should be more atoms in the source than in the target. And the clean way to formulate some such assumption is this one.
Yeah, that's fine.
Thank you. Okay.
I have another question. So from here, the value of T naught that we get, and so basically phi naught characterizes both Monge and Kantorovic's program, right? In this case, when the assumptions are right. So when we actually plug in these values of optimal T naught and optimal gamma naught, do the two programs evaluate to the same value?
Yes, and that will precisely be the Wasserstein distance between mu and nu. Yeah.
Okay, okay.
I guess I have a small question. So
Yeah.
I guess this thing you wrote about so that for any pair of points x and y for a convex function, it is the case that x minus y inner product gradient of phi at x minus gradient of phi at y. These two things, yeah. So this inner product is always non-negative, and this I guess is equivalent to convexity, right? So phi is convex if and only if this happens. So
Yeah,
yeah.
that's right.
So yeah, but then somehow yeah. So while this can prove that you have cyclic monotonicity, you somehow get this stronger thing also that that any function is a gradient of a convex function only if this works. So you actually get a lot more out of cyclic monotonicity as compared to just the thing about.
Yeah, so I think maybe so monotonicity is like a univariate notion, right? So I don't know, it doesn't make sense to say that this condition is true. So I think of usual monotonicity, which is just this condition. If x is bigger than y, then f of x has to be bigger than f of y. That's a way of saying f is a monotone function. It's only a well-defined notion in 1D. In more than 1D, there's no meaning to saying either of these two things. So you need some sort of inner product expression, and that is cyclical monotonicity. Or that is one.
Yeah. Okay, great. Thanks. I think there's one more question.
Okay.
So in that theorem, I think Brenner's theorem. So why does again, like, why does that map has to be a gradient of a convex function? And also, I'm also like, oh, okay, all right, yeah, all right, that's the question.
Why does it have to be the gradient of a convex function? Yeah, so I mean, maybe that is the content of the theorem. Like one has to prove it maybe to answer this question. But all I'm saying is, for intuition, you should think of the OT map. If I said it optimizes this objective, it should be somehow a nice map in the sense that it shouldn't do silly things. It shouldn't move mass somewhere and then, I don't know, it shouldn't be suboptimal. And one way to capture this fact that it is not suboptimal is to say it should be monotonic in some appropriate sense of monotonicity. And this appropriate sense of monotonicity is that it should satisfy cyclical monotonicity. And then the fact that it's the gradient of a convex function is some theorem in analysis that just says every cyclically monotone map is the gradient of a convex function. So you should think of it as, okay, because it's an optimal map, it should satisfy some nice notion of monotonicity. And then everything that satisfies that notion of monotonicity is the gradient of a convex function.
And also, like, can there be any other map? So any other map other than T0, which is also a gradient of a convex function, and it satisfies the same property, like T0 converts mu to nu.
No. So there are many maps potentially that convert mu to nu, but if it is the gradient of a convex function, then it is it'll be equal to T0 mu almost everywhere. So that is somehow there is some uniqueness, and there's a way that, so if I give you a map and I tell you that it's the gradient of a convex function, you know that it's the OT map. So there are some stronger so there aren't any other gradients of convex functions that aren't exactly equal to T0 that push mu onto nu.
So you were saying like there is some one mapping from every pair mu nu to the set of convex functions up to constants, like.
Correct. Yeah, so mu nu that satisfy the conditions of this theorem, there is a mu almost everywhere unique convex function whose gradient, so unique up to shifts, whose gradient will give you a map. And it's a one, yeah. So everything is unique in this sentence.
Yeah, I guess what's going on, it's the property of monotonicity. It's guaranteeing that there are no trivial cycles along which you can move things around and decrease the cost.
Mm-hmm.
I guess that's what it's saying, right? Because here, if there was a cycle where the quantity was negative, then you could just add it to your map and you could have a smaller cost map.
Yeah, I guess,
yeah.
yeah, add it or remove it. So
Yeah.
something you like what you said is true, yes.
And therefore, in some sense, it characterizes the right thing. I guess this same thing which happens in min cost bipartite matchings, right? That so matching is optimal in terms of cost if and only if there's no cycle along which you can improve. I guess it's
Yeah.
the continuous analog of the same thing.
Yeah, exactly. It is. So yeah, except yeah, this one is, I don't know. In this form, it is very specific to the squared Euclidean cost. I think your statement maybe actually applies to more general costs, but it wouldn't have these nice convexity relationships, except for the squared Euclidean cost.
But even otherwise, I could still state this property of monotonicity, and I could still just work with that. That maybe.
Yeah.
Okay.
That's right.
Yeah. Great. Thanks, Shivraman. I guess to see you tomorrow, and thanks for the nice lecture.
Sir, one last doubt. The Brenner's theorem and everything, is it only for the p equal to 2 case, the squared Euclidean laws?
Yeah.
Oh,
yeah, that's right.
Okay.
You will be visiting this again tomorrow?
Yeah, I'll start with the duality part. I might recap quickly. Yeah.
Okay.
Okay. Okay. Thank you all. And see you tomorrow.
See you.